Hello everybody, I welcome you all once again to my third lecture on DC transients. In my previous two lectures, we have seen the introduction regarding DC transients and initial conditions. We have also solved some tutorials on initial conditions. In today's lecture, we shall see how to derive the complete response of a series RL circuit using differential equation method and Laplace transform method. So derivation of the complete response of series RL circuit can be done in two methods. One is using differential equation method, second one is by using Laplace method. So here series RL circuit we have two types. One is source free RL circuit and another one is source driven RL circuit. So first we shall derive the expression for source free RL circuit using differential equation method. So this is the circuit diagram for deriving the expression for the complete response of source free RL circuit. So here initially we assume that the switch is at position 1 for very long time, and at t is equal to 0 the switch is moved from position 1 to position 2. In this case we assume that when the switch is at position 1 the circuit is at steady state, and we know that at steady state the inductor will act as short circuit. So therefore when the circuit is at position 1, we have a voltage source which is connected in series with R and L. Since at position 1 the circuit is in steady state, the inductor will act as short circuit. Therefore for t less than 0, that is when the switch is at position 1, the circuit that we get is the inductor will act as a short circuit. So this is R, this is V, and in this case the current is nothing but I of 0 minus. So I of 0 minus, that is the initial current, is nothing but V by R. Let us assume to be some I naught. We already know that the inductor property is to not allow any sudden changes in current. So when we move the position of switch from position 1 to position 2, the values of current as well as voltages will change instantaneously, but due to the behavior of inductor the value of current flowing to the circuit will not change. So that is I of 0 plus, that is immediately after switching the current flowing through the inductor is same as the current flowing through it before switching, which is nothing but in this case it is V by R, and that is I naught. At t greater than 0, that is after the switch is moved from position 1 to position 2, so the position 2 there is no element connected here, this is like a short circuit, so you will have a resistor in series with an inductor. Here we have R and here we have L, and the current is I of t. So now in order to get the expression for complete response we have to apply KVL to this equation. So when I apply KVL to this circuit I'll get R into I of t plus L into di by dt is equal to 0 since there is no source connected. That is why this is called source free. So dividing by L throughout, I will get di by dt plus R by L into I of t is equal to 0. Here the coefficient of I of t is R by L. So that is why I will multiply e power R by L into t on both sides. So when I multiply e power R by L into t on both sides, I will get e power R by L into t into di by dt plus R by L into I of t into e power R by L into t is equal to 0. So this expression I can write as d of I of t into R by L into t is equal to 0. Because if I consider this I of t as u and this e power R by L into t as v, we know the formula of derivative of uv. It is u into v dash plus v into u dash. U into v dash. I of t into the derivative of this is nothing but R by L into e power R by L into. So that is this term plus e power R by L into t into derivative of this term, that is d by dt of I of t. So this expression I can write as d of I of t into e power R by L into t. Now integrating on both sides. So if I integrate on both sides, this derivative term will get cancelled and I will remain with I of t into e power R by L into t is equal to, so since right hand side you do not have any term, after integrating you will get a constant k. So therefore the expression for I of t is I of t is equal to k into e power minus R by L into t. So in order to find the value of the constant k, we should use initial conditions. We know that I of 0 minus, in this case we have obtained, which is equal to I of 0 plus v by r. So applying this condition to the above equation. So at t is equal to 0 plus, the above expression becomes I of 0 plus is equal to k into e power minus 0, because this value becomes k since e power 0 is 1. So therefore I of t is equal to k, which is equal to I of 0, but I of 0 value is v by r, so k value is also v by r. So it is v by r e power minus r by L into t. This I can write as I of t is equal to v by r into e power minus t by tau, where tau is nothing but L by r and is called time constant of RL circuit. So this is the expression of the complete response of source free RL circuit using differential equation method. So we will see later what is the significance of this time constant tau. Now we shall derive the same expression using Laplace domain method. Let us consider the same circuit. Now in this case also, since we have already derived the initial conditions, I will not repeat again. So in this case, the initial condition, that is I of 0 plus is equal to I of 0 minus, which we have obtained as V by R. So at t greater than 0, you know that we will get a circuit which is R and L in series with no source, and the current is I of t. So when I apply KVL to this loop, I will get R into I of t plus L into di by dt is equal to 0. So this I can rewrite as, if I divide by L throughout, we'll get di by dt plus R by L into I of t is equal to 0. Now let us apply Laplace transform to this expression. So we all know that if f of t is a function, then Laplace transform of a derivative function is not f of t is nothing but s into f of s minus f of 0. So instead of f of t, I have I of t here. So if I apply Laplace transform, I will get s into I of s minus I of 0. So s into I of s minus I of 0. So in this case, I will take of I of 0 plus, since it is an initial condition, into plus R by L into I of t becomes I of s. I of s is equal to 0. So if I take I of s common, so I of 0 plus value, we know it is nothing but V by R. So this above expression is s into I of s minus V by R plus R by L into I of s is equal to 0. So if I take I of s as common, then I will get s plus R by L, which is equal to V by R. Then I of s is equal to V by R divided by s plus R by L. So applying inverse Laplace transform. So when I apply inverse Laplace, I of s becomes I of t. This is in the form of 1 by s plus a. So inverse Laplace of 1 by s plus a is nothing but e power minus at. So V by R is a constant, V by R into e power minus s plus a. Instead of a, I have R by L. So V by R into e power minus R by L into t. So this I can write as I of t is equal to V by R into e power minus t by tau. So as you can see that the expression that we have obtained is same irrespective of the method we use, where tau refers to a time constant which is L by R. So suppose the voltage across resistor is VR of t and voltage across inductor is VL of t. So we'll try to also derive what is the expression for VR of t and VL of t. So voltage across resistor, as we all know, is I into R, and voltage across inductor, as we know, is L into di by dt. So this value I of t, as you know, I of t, we have got the expression v by r into e power minus r by l into t. So I of t is v by r into e power minus t by tau into r. So r will get cancelled. So the expression for Vr of t is v into e power minus t by tau. So next VL of t, L into d by dt of I of t, which is v by r into e power minus r by l into t. So v by r is a constant. So L into v by r. Derivative of this expression will give you e power minus r by l into t into minus r by l. So r will get cancelled, l will get cancelled. So the expression for voltage across inductor will be nothing but minus v into e power minus t by tau. So we have obtained the expressions for I of t, Vr of t and Vl of t. Let us try to draw the responses of these three expressions. So let us consider x-axis to be time and y-axis to be I of t. So from the expression of I of t, we can clearly say that the response will be exponentially decreasing from the value v by r. So the steady state value will be v by r. That is, if suppose this is the steady state value v by r, so the response will exponentially decay from v by r. Similarly, if I consider x-axis to be time and y-axis to be both Vr and Vl. So from the expression of Vr, I can say that the steady state value is V and the response will decrease exponentially from V. Similarly, if I consider VL, as you can see here, it will exponentially increase from minus V. That is, if I consider this as positive scale and this as negative scale, suppose this is plus B and this is minus B. So from plus B, as we have seen that it is exponentially decaying. So from plus B, it is exponentially decaying. And from minus V, it is exponentially. So from minus V, it will approach towards 0. So this is the expression for Vr of t and this is the expression for Vl of t. So next, let us derive the expression for complete response of source driven RL circuit. So this is the circuit configuration for source driven series RL circuit. So here, as you can see, the switch is closed at t is equal to 0. That means the switch is initially open. So when switch is open, we know that the current flowing will be 0. So in this case, I of 0 minus is equal to 0 amps. So but the inductor property is, as we know, it does not allow any sudden changes in current. So the current flowing through inductor before and after switching will be same. So I of 0 plus is equal to I of 0 minus, which is nothing but 0 amps. So at t greater than 0, so after we close the switch, let us apply KVL to this circuit and we'll get R into I of t plus L into di by dt is equal to V. So dividing by L throughout, I will get di by dt plus R by L into I of t is equal to V by L. So here we have to derive the expression for I of t. So here again, once again, I have the coefficient R by L. So I am going to multiply e power R by L into t on both sides. So if I multiply e power R by L into t on both sides, I will get e power R by L into t into di by dt plus R by L into t, I of t into e power R by L into t is equal to V by L into e power R by L into t. So again, this expression is in the form of UV formula. So I can write as d of I of t into e power R by L into t, which is equal to V by L into e power R by L into t. So I will integrate on both sides. So if I integrate on both sides, the differential term and integral term will cancel each other. So I will get I of t into e power R by L into t is equal to integral V by L into e power R by L into t. So if I integrate this, V by L is a constant. So integral e power at is e power at by a. So it is e power R by L into t into L by R, plus we will have some constant k. So here L will get cancelled. So I of t into e power R by L into t is equal to, we got V by R into e power R by L into t plus some constant k. So I want the expression for I of t, so I'll send this term to right hand side, and this expression becomes I of t is equal to V by R into e power R by L into t into e power minus R by L into t plus constant k into e power minus R by L into t. So the term e power R by L into t on left hand side, when we send it to right hand side, it becomes e power minus R by L into t. So this will get cancelled. So I of t is equal to, I will be left with V by R plus k into e power minus R by L into t. So here again the constant k can be found out by using initial conditions. We know that at t is equal to 0 plus, I of 0 plus is equal to 0. So if I substitute this condition in the above expression, so I of 0 plus is equal to V by R plus k into e power 0. So from this value obviously is equal to 0, since I of 0 is 0. So from this k value is equal to minus V by R. So this value, if I substitute in this expression, I'll get my expression for I of t. I of t is equal to V by R. So instead of k, minus V by R into e power R by L into t. So therefore I of t is equal to V by R. If I take common, it is 1 minus e power minus R by L into t, or I of t is equal to V by R into 1 minus e power minus t by tau, where tau is the time constant, which is L by R for series RL circuit. So here also we shall derive the expressions for VR of t and VL of t. So VR of t, voltage across resistor, is R into I of t. So R into V by R minus V by R into e power minus R by L into t. So if I take, so RR will get cancelled. So VR of t is equal to V into 1 minus e power t by tau. Similarly, VL of t is L into di by dt, and I of t, as we know, is V by R minus V by R into e power minus R by L into t. So if I differentiate, I'll get VL of t is equal to L into, since V by R is a constant, the derivative of a constant is 0, minus V by R into the derivative of e power minus R by L is nothing but e power minus R by L into minus R by L. So if I simplify, I'll get V by L of t is equal to, so here RR will get cancelled and LL also will get cancelled. So I'll be left with V into e power minus t by tau. So if I draw the expressions for I of t, y-axis if I consider I of t, x-axis as t, so we have got the expression I of t is equal to V by R into 1 minus e power minus t by tau. So the steady state value is V by R. So hence we have 1 minus e power minus t by tau. It means that this value is exponentially increasing till V by R. So if the steady state value is V by R, then I of t is exponentially increasing till V by R. So if I consider VR and VL on y-axis and time on x-axis, here the steady state value is V, so it is exponentially increasing to V. So the expression for VL, it is exponentially decreasing from V. So if I consider this as V, so VR of t is exponentially increasing and VL of t is exponentially decreasing. So this entire analysis of response is based on assumption that the initial current is 0. But at all cases we will not have the initial current to be 0. So hence let us try to derive a more general expression in which all cases will be possible. So let us consider this expression that we have got earlier. So I of t, let me take a new page. So I of t, previously we have obtained as V by R plus K into e power minus R by L into t. So it is V by R plus K into e power minus R by L into t. So V by R is nothing but the steady state value. So this I can write as I of infinity. As you know, at t is equal to infinity indicates steady state value. So since V by R is a steady state value, I can write that as I of infinity. So if I substitute t is equal to 0, so I of 0 is equal to nothing but v by r plus k. So from this I can write k is equal to I of 0 minus v by r, or in other words I of 0 minus I of infinity. So from this expression I of t is equal to v by r, I can write as I of infinity plus, instead of k I can write I of 0 minus I of infinity into e power minus r by l into t. So this is the general expression of source driven RL circuit. Hence this expression is valid for all conditions, that is even the initial condition is 0 or the initial condition is some I0. For all such conditions this general equation is valid. So now let us try to derive the same expression using Laplace transform method. So the initial condition is I of 0 plus is equal to I of 0 minus is equal to 0, and the circuit configuration is same, that is series RL circuit, and the switch is closed at t is equal to 0. So applying KVL we get R into I of t plus L into di by dt is equal to V. So if I divide by L throughout, di by dt plus R by L into t, I of t is equal to V by L. So applying Laplace transform on both sides, I get, instead of di by dt I'll get s into I of s minus I of 0 plus R by L into I of s is equal to, so the Laplace transform of a constant is 1 by s, a by s, so it is V by L to 1 by s. So therefore here I of 0 is anyhow 0, so therefore if I take I of s as common, I'll get s plus R by L is equal to V by Ls. So therefore I of s is equal to V by L divided by s into s plus R by L. So applying partial fractions, this is a by s plus b by s plus R by L. So on applying partial fractions, a is equal to, so I'll get V by L by, so in order to get a value, consider the entire expression except s plus R by L, and substitute s is equal to 0. So you will get V by R. For b value, consider the entire expression except s plus R by L. So it is V by L divided by s, and substitute s is equal to minus R by L. So you will get minus V by R. So s is equal to, a value is V by R, so it is V by R by s. B value is minus V by R minus V by R by s plus R by L. So applying inverse Laplace transform, so I of t is equal to 1 by s, inverse Laplace of 1 by s is 1, so it is simply V by R. Inverse Laplace of 1 by s plus a is e power minus at, that is V by R into e power minus R by L into t. So this again I can write as I of t is equal to V by R into 1 minus e power minus t by tau. So this is the derivation of the expression for complete response of source driven RL circuit using Laplace transform. So now let us see what is the significance of the time constant. So in a series RL circuit, the time constant tau is equal to L by R. So in this, the expression for I of t we have obtained as V by R into 1 minus e power minus t by tau. The expression for VL of t we have obtained as V into e power minus t by tau. So let us substitute t is equal to tau. So if I substitute t is equal to tau, then I of t or I of tau becomes V by R into 1 minus e power minus 1. That is, it becomes 0.6321 into V by R. Or in other words, I can tell that I of tau is nothing but 63.21% of V by R. Similarly, if VL of tau is equal to V into minus 1, therefore this becomes 0.3679 into V, or 36.79% of V. So from this two conditions, we can define time constant of RL circuit as it is the time taken for the current flowing through inductor to reach 63.21% of the steady state value. So we know that V by R is a steady state value. So here in this case, the steady state value is V. So from the graph we can see, so for the current response the steady state value is V by R, and for the voltage response the steady state value is V. So the time constant I can also define as it is the time taken for the voltage across inductor to fall to 36.79% from its initial steady state value. So in this way we can define the time constant of an RL circuit. So this ends my lecture on derivation of complete response of source driven as well as source free series RL circuit using both differential as well as Laplace method. So in my next lecture we shall see some tutorials based on source free and source driven series RL circuit using differential as well as Laplace method. Thank you.